Hi everybody, happy Wednesday. This is Jannel and Henry and Vincent, and we're going to be doing chapter 12. And chapter 12 consists of curved space vector calculus, where it covers vector continuity, projectile motion, unit tangent vector to a curve, smooth curves to find the tangent line to a curve, unit normal vector and binormal vector, tangent plane, normal plane, and oscillating plane, curvature, acceleration, finding curvature, and more in acceleration, and then we're going to learn some basic parametrized curves, and then we're going to reparameterize a curve with respect to arc length, and then we're going to learn a little bit about vectorial mechanics and dynamic of rotations. And so if we think of C as being traced out by a moving particle whose position at time t is f of t, g of t, and h of t, and we consider the vector function r of t, where f of t and g of t and h of t, then r of t is the position vector of the point P of f of t, g of t, and h of t on C. Any continuous vector function r defines a space on the curve C that is traced out by the tip of the moving vector r. And then so we see that this is the tip of the moving vector r, and as it proceeds along the moving curve of C. Now we suppose that C is a curve given by a vector function r of t, where t is between a and b, and r prime is continuous and C is traversed exactly once as t increases from a to b. And so what it's saying, as it goes from r of t, it goes from a, and then b is not shown, but it goes from a to t. This is the curve, or the length shown, and then this is the arc length that we are trying to find, which is defined as s of t. And then we find that by finding the derivative of each of x and y and z over the square root. Thus, s of t is the length of part of C between r of a and r of t. If we differentiate both sides, and we get ds over dt equals the magnitude of r prime over t. And then so we're going to do some arc length problems. And so if we're given r of t, which is t squared, t cubed, and t to the fourth, where t is in between 0 and 2, we find r prime, which is 2t, 3t squared, and 4t cubed, and then we find the magnitude of r prime t, which is 2t squared plus 3t squared squared, and then 4t cubed squared, all under the square root. And then so we find the length of that, and we take the integral of it from 0 to 2, which comes out to 18.6833. And another problem for that would be if we're given r of t, and then our coordinates are sine of t, cosine of t, and tangent of t, where t is from 0 to pi over 4. And if we take r prime of t, we have cosine t, negative sine t, and secant squared t. And if we find the magnitude of that, that becomes cosine squared t plus the negative sine squared t plus secant squared t squared, all under the root, which simplifies to 1 plus secant 4t, all under the square root. And then if we take the integral of that from 0 to pi over 4, we come out with 1.2780. And so it is useful to think to reparameterize a curve with respect to arc length, because arc length arises naturally from the shape of the curve and does not depend on a particular coordinate system. And so what it means is that the arc length follows the shape of the curve. So instead of drawing a straight line and then figuring out that way, we can just find the length of the curve. And the parameterization r of t is called smooth on an interval I if r prime is continuous and r prime of t does not equal 0 on I. A curve is called smooth if it has a smooth parameterization. And so it is shown here for the curve r of t, a cosine t, b sine of t, bt is a circular helix. And you can see it looks like it intersects itself, but it doesn't, because we have that extra z-axis. And so we just have a helix. And then so another way to see this is an example of a twisted cube, where r of t equals t, t squared, and t cubed. And then if we see over here, when we graph it, it looks like this. And then if we add the z-axis to it, it looks lifted, just like how we saw in class with the fly in the wall problem, where it starts from one corner and then moves upwards and then lands on the other corner of the room. And then part C shows the result of rotating the box to give another viewpoint. Parts D, E, and F shows the views we get when we look directly at the face of the box. In particular, part D shows the view from directly above the box. It's the projection of the curve on the xy plane, which is the parabola y equals x squared. And then part E shows the projection on the xz plane, and the cubic, which is the cubic curve z equals x cubed. And then to see some examples of this, of where, like on which axis it would extend out to, we have some of these. And so we see that we have x equals t cosine t, y equals t, and then z equals t sine t, and t is greater than 0. And then so we see that x squared plus z squared would equal t squared. Let me write this out. T squared cosine t, or cosine squared t, plus t squared sine squared t. And then you can see that cosine squared plus sine squared equals 1. So it just equals t squared. And then we see that t squared is similar to y squared. And then so we can say that that equals y squared. And so the curve lies on the circular cone x squared plus z squared equals y squared, which means that the y-axis would extend out. So you have a cone extending out over the y-axis. Another example of this is where we have x equals t, y equals 1 over 1 plus t squared, and z equals t squared. And then at any point on the curve, we have z equals x squared. And so the curve lies on a parabolic cylinder parallel to the y-axis. And we see that. Parabolic parallel to the y-axis, and we have the cylinder going up. And in this problem, it's similar to the problem we did a couple slides ago, where x equals cosine 8 of t, y equals sine 8 of t, and then z equals e to the 0.8t, where t is greater than 0. And then so over here again, we see that x squared plus y squared equals cosine squared 8t equals 1. And then that is because cosine plus sine squared equals 1. And then so the curve lies on a circular cylinder with the x-axis, or the z-axis as the axis. And so we have a circular cylinder going up along the z-axis. And so, if r of t equals f of t, g of t, and h of t is the position of particle at any time, then with a very small change in t, the position vector changes to r of t plus change in t, which expands, or you can distribute it within it, which comes out to f of t plus change of t, and then g of t plus change of t, and then h of t plus change of t. So the change in position is the change of r of t, which is r plus t plus change of t, minus r of t. And then so that comes out to the average speed of r t plus change of t minus r of t over the change of t, which gives us the instantaneous speed. So the vector function r of t is said to be continuous at t equals t naught. If every epsilon is greater than 0, there corresponds a number such that r of t minus r of t of naught is less than epsilon of t minus t naught. And so if r of t equals f of t, g of t, and h of t, then velocity and acceleration vector is just the r prime of t and r double prime of t. And so we see that, or it comes out to this and over here. And then if we see an example of that, and we're given r of t is r cosine omega t, r sine omega t, and 0, and then when we take the r prime of t, we get omega in the front, and then if we take the double prime, then we come out with omega squared and omega squared in each of them. And if we see that this equation is similar to over here, and the only difference is that we have this. And then so we can summarize that as omega squared to the r of t. And then since r double prime of t, it is organized over here, and acceleration and position are in the same direction, which is shown in this graph right over here. And since force is a product of mass and acceleration for constant mass, then force equals m r of t omega squared. And so an example of this would be, we're going to do a little example. The position vector of an object moving in a plane is given by r of t, t cubed plus t squared. Find its velocity, speed, and acceleration when t equals 1. And so we are given v of t, where we find r prime, which is 3t squared plus 2t, and then we take the r double prime of that, which is 6t plus 2. And so the speed would be the magnitude of velocity, and so that would be the first prime of r, and so it would be 3t squared plus 2t squared, all under the square root. And then so when we have t equals 1, then we plug it back in, and then we have v1 is 3i plus 2j, and the acceleration of 1 is 6i plus 2j. And then we see that the speed of 1 is the square root of 13. And then another example problem of this, when we're given r of t equals t squared, e to the t, and t e to the t. And so we find velocity again by taking the first prime of r, and it comes out to 2t e to the t, and then 1 plus t e to the t. And then we take the derivative of that, of v, which is r double prime, to find acceleration, which is 2 e to the t, and then 2 plus t e to the t. And then to find the speed, we take the magnitude of velocity, and so we take all of that and add it all and put it all under the square root. And so now we have projectile motion, where if acceleration and initial velocity and position are given, one can find the velocity and position vector by simple integration. Let's turn the axes in a direction so that the particle moves on the xy plane. Then F equals ma, and acceleration is 0 and to negative g. And it's 0 to negative g because when we're thinking about gravity, we're not moving in the x direction, we're just moving in the y direction, and it would be negative because we're coming back towards the Earth. And then the unit is meters over seconds squared. And so we have velocity, which is v cosine theta, comma, negative gt plus v sine theta. And then if we take the integral of that, then we are given an extra t and then plus x naught. And then over here, it's negative g over 2 t squared plus v sine t plus y naught. And then so an example of this would be a projectile is fired with muzzle speed 150 meters per second and angle of elevation 45 degrees from a position 10 meters above ground level. Where does the projectile hit the ground and with what speed? And so if we place the origin at ground level, then the initial position of the projectile is 0, 10. And so we need to adjust equations by adding 10 to the expression. And so we have v naught, which is 150 cosine, and then the pi over 4 of 45 or the cosine of 45 degrees is pi over 4, and then so nt, which comes out to this for our x component. And then for y, we add 10 to 150, so it's 10 plus 150, and then sine pi over 4t minus 1/2 9.8, which is the force of gravity, t squared, which comes out to right over here. And so impact occurs when y equals 0. And so we set 4.9 t squared minus 75 root t, 2t minus 10 to 0. And then solving for that, we get 21.74. And then going back and plugging that back into this equation, t, we get x equals 75 root 2 times 21.74, which is 2,306. So the projectile hits the ground about 2,306 meters away. And if we need to find the velocity, then it's v of t, which is the r prime, and so it's 75 root 2 plus 75 root 2 minus 9.8 t. And then to find the speed of that, it's just the magnitude of the velocity. which is 151 meters per second. And then we are given two methods to graph parametric equations in 2D space. The first one is a simple one where you simply just plot x and y and then you see what you get. This one is a little bit tedious and it takes a little bit longer since you have to plot every single individual point. And the second method would be to eliminate the parameter t and then write the equation in terms of x and y only. And so we have x and y in terms of t, and then so if we bring v naught cosine theta over to x of t, we have t, and then plug it into the y of t equation where we get over here, and simplified it comes out to negative g over 2 v squared naught cosine squared theta x squared plus tangent theta x. And this quadratic equation with a negative coefficient of x squared is a concave down parabola and guarantees object with mass and low velocity will return back to Earth. Objects with high velocity, more than 7 miles per second, can escape the Earth's gravitational field, which is a bit over 30 times the speed of sound. And so now we're going to learn about unit tangent vectors to a curve. And so a unit tangent vector is the direction velocity of the particle at a given time. It can be calculated as r prime of t over the magnitude of r prime of t. And to find the tangent line to a curve, we have 3 steps. The first one is to find r prime of t and then the unit tangent vector. And then the second step is at the given point, find time t. And then use t to find t of t as a directional vector and write the equation of the tangent line. And so we can see this in an example. And so we're going to find the tangent line to a parametric equation, r of t, 2t cubed minus 1, negative 5t squared plus t, and 8t plus 2 at point P, which is 1, negative 2, 10. And so for the first step, we're going to find r prime of t, which is 6t squared, negative 10t, and 8. And then r prime of 1 is 6, negative 10, and 1, or 8, I'm sorry. And then t of 1 comes out to 6, negative 10 over 8, and then the magnitude, which is root 200. And then take all of this, and then we plug it back, or we find the equation of the line. And so we have 1 plus 6t, and then negative 2 plus 10, minus 10t, and then 10 plus 8t. And so the normal and binormal vectors, at a given point on a smooth curved space r of t, there are many vectors that are orthogonal to the unit tangent vector t of t. We single one out by observing that because t of t equals 1 for all of t, we have t of t times t prime of t equals 0. So t prime of t is orthogonal to t of t. Note that t prime of t is itself not a unit vector, but at any point where curvature does not equal 0, we can define the principal unit normal vector n of t as t prime of t over the magnitude of t prime of t. The vector b of t equals t of t times n of t, which is the cross product, and is called the binormal vector. It is perpendicular to both t and n and is also a unit vector. And a way to simplify this or organize it in a graph would be over here. And you know what we love, example problems. And so we find the unit normal and binormal vectors for the circular helix r of t equals cosine t plus sine t plus t. And so first we find r prime of t, of course. And so that comes out to negative sine t plus cosine t. And then the magnitude of r prime of t is root 2. And then so using those two, we find t of t. And so we take the first part, r prime of t, and then over the magnitude. So it just comes out to 1/2 over, or times negative of the r prime of t. And then to take the r prime of t, you just find this. And then so it comes out to negative cosine t minus sine t. And then the magnitude of that would just be 1 over root 2. And then from there, we find the n of t, which is t prime of t over the magnitude. And so that is just over here. It cancels out. And so it comes out to, or the 1 over root 2's cancels out. So it comes out to negative cosine t minus sine t. And so when you organize that, it comes out to negative cosine t minus sine t 0. This shows that the normal vector at any point on the helix is horizontal and points towards the z-axis because this is 0. And the binormal vector, when we find it, is bt and the cross product of t and n, which is, bring the 1/2 out there, negative sine t cosine t1, and I'll plug those in, and it comes out to 1 over root 2 sine of t minus cosine of t and 1. And so another example of this would be if we're given r of t, which is t and t squared. And then so we find r prime of t, which is 1 and 2t, and then r double prime of t, which is 0 and 2. They are not orthogonal to each other except at t equals 0. So let's look at the unit tangent and normal vectors. And so if we find the unit tangent vector, which is r prime of t over the magnitude of r prime of t, comes out to over here. And then we find the unit normal vector, which comes out to this. And then if we take the tangent vector and do the dot product with n of t, we get 0. And so b of t, when we plot it out, it's 1, 2, t, 0, negative 2t, 1, 0, times 1 over 4t squared plus 1, because these two under the root takes out the root. And so we are left with 1 over 4t squared plus 1, 4t squared plus 1k, which is 0, 0, 1. This shows that the binormal is independent of time and is always constant. Therefore, the curve is in 2D, because these two first points are 0. And another fun example of this, find the unit tangent and normal vector of the unit normal vectors tt and nt, and use that to find the curvature. And so we're given r of t, which is t, 3 cosine t, and 3 sine t. And so we're given r of t, and so we find the r prime, and then the magnitude of r prime, which comes out to root 10. And so taking that, we can find the unit tangent vector, which is, of course, r prime over magnitude of r prime, and so that comes out to over here. Or if you want to keep the constant out, leave it over here. If you want to multiply it in there, and then from there you find the t prime of t, which comes out to this. Find the magnitude of it, which comes out to 3 over root 10. And then using those values, we find the normal vector, which is the unit tangent vector prime over the magnitude of the unit tangent vector prime. And then it comes out to 0, negative cosine t minus sine t. And then to find the curvature of that, we're given the formula of magnitude of t prime of t over the magnitude of r prime of t. And so that's 3 over root 10 over root 10, which is just 3 over 10. And so after we've just done so many wonderful examples, this is a way for us to organize it and help look at it better so that we can learn it. Okay. And so the plane determined by the normal and binormal vectors n and b at point P on a curve C is called the normal plane of C at P. The circle that lies in the oscillating plane of C at P has the same tangent as C at P and lies on the concave side of C and has radius P equals 1 over k, which is the reciprocal of the curvature. This is called the oscillating circle of C at P. It is a circle that best describes how C behaves near P and is sharing the same tangent, normal, and curvature at P. And so we're talking about the point P right here, and then this is the oscillating circle as it moves along the curve C. And so, obviously, we love examples, so we're going to find the equations of the normal plane and oscillating plane of the helix of the point P, 0, 1, and pi over 2. And so the normal plane at P has normal vector r prime of pi over 2, which is negative 1, 0, 1. And so in an equation, we're going to plug it in, which is negative 1 x minus 0, which is from here, and then 0 y minus 1, and then 1 times z minus pi over 2, which is equals 0. Or to organize all of this better, it comes out to z equals x plus pi over 2. And the oscillating plane at P contains the vectors t and n, so its normal vector is t times n equals b. And so from the earlier example that we did, we found that b of t equals 1 over root 2 sine of t minus cosine t of 1. And so if we plug in pi over 2 of that, we get 1 over root 2, 0, 1 over root 2. And so in a way to see that would be a simpler normal vector is 1, 0, 1. And so to plug in the equation for that, that would be 1, x minus 0, and then 0, y minus 1, and then 1, z minus pi over 2 equals 0. And then organize that again, it would be z equals negative x plus pi over 2. And another awesome example to find the equations of the normal plane and oscillating plane of the curve at a given point, where x equals 2 sine 3t, y equals t, z equals 2 cosine 3t, and we are given 0, pi, and negative 2. And so 0, pi, negative 2 corresponds to t equals pi. And so r of t equals 2 sine 3t, t, 2 cosine 3t. And so when we find t, the tangent vector, we take r prime of t over the magnitude of r prime over t, and it comes out to 1 over root 37 times 6 cosine 3t, 1 negative sine 3t, or negative 6 sine 3t. And if we plug in pi to that, it comes out to 1 over root 37, negative 6, 1, 0. And it's a normal vector for the normal plane. And so negative 6, 1, 0 is also normal. Thus, the equation for the plane is we plug that in to these points. So it would be negative 6, x minus 0, and then 1, y minus pi, and then 0 times z plus 2 equals 0. Or simplify that, and we get y minus 6x equals pi. And then from there, to find the normal unit normal vector, we take t prime of t, which comes out to 1 over root 37, negative 18 sine 3t, 0, negative 18 cosine 3t, and we take the magnitude of that, comes out to 18 over root 37. And so since we have those two components, we can find the normal unit vector. And so it would be t prime of t over the magnitude of t prime of t. And then so that comes out to negative sine 3t, 0, negative cosine 3t. And so if we plug in pi to that, we get 0, 0, 1. And if we plug in, we found earlier that when we plugged in, or we plug in b, or pi to b, and so we find 1 over root 37, negative 6, 1, 0, and cross it by 0, 0, 1, we get 1 over 37, 1, 6, 0. And since b of pi is normal to the oscillating plane, so is 1, 6, and 0. And so an equation for the plane is 1 times x minus 0 plus 6 y minus pi plus 0 z minus 2, or z plus 2 equals 0. Or to simplify that again, we get x plus 6y equals 6, x plus 6y equals 6 pi. Okay, so we have learned about the first part of chapter 12, and now we're going to have Vincent take it over, and he's going to teach us about acceleration, finding curvature, and he's going to show us some examples. Take it away, Vincent.
Hello everyone, so I will be covering the last part of chapter 12. So the last part of chapter 12 consists of reparametrizing a curve with respect to arc length, quadratic surface, and vectorial mechanics. And there's a few show that exercises in between. I'll just go it through because it's basically on the quiz before, so I bet everybody is pretty familiar with it. Okay, so the first subject, reparametrizing a curve with respect to arc length s. The definition of this is just redefining the curve in terms of a different parameter. So it's pretty easy, the concept. It's just changing t into arc length s, the variable t to s. So step one, we have r of t, so we have to find r prime t. in absolute value. And step 2, evaluate s equals, evaluate the arc length, basically. So we make integral 0 to t, absolute value, r prime t star, dt star. Then we find the inverse of s equals integral 0 to t, absolute value, r prime t star, dt star. So, and then making it into t equals something s. So in this case, we can actually just plug it back in, and then we know that's what the step 3 is for. So step 3 is replace the original t in r of t in terms of s. So we know t is something s. We just plug this back in, and then we get a reparametrized reparametrized curve. Here's one example. So basically just reparametrizing this function r of t. So the first step is making r prime t. R prime t will be equal to, I'll just make fast calculations here. Just jump down into this part. Okay, I'm writing a little too slow. Right. So this is r prime t. Yeah, this is r prime t. And we have to find r prime t in an absolute value. So this would be 1 plus t squared, 2. So I know I skip a lot of steps, but you can do the calculations by yourself because it's tedious, but it's straightforward. And then the second thing is find the arc length, s. 0 to t, this thing, t squared dt, which makes it into 2 tangent inverse x, because it's obvious, right? 1 plus 2 squared. So, oh, sorry, wait, it's s. So once you find this relationship, no, sorry, this is t. Once you find this relationship, you can make it into t something s, the form of t something s, which is t tangent of s. This is what we want. And so we plug it back in to this thing. This thing comes out and use some trig identities. You fix it, and at the end, it's going to be like this, which is really, really clean and straightforward for a reparametrized function. So in this case, we reparametrize it I mean, it's more clear to know about the identities for this one other than the original function, this one. So this is for the first. And here's 3 other problems. R of t, sine of t, r of t equals sine of t, t cosine of t. So show that the first one, curvature in an absolute value equals r double prime s in an absolute value. And second is r prime s dot r double prime s equals 0. And the third one is r prime s dot r prime s will equals to 1. So the first one I already had a head start over here. We do one derivative and then make it into absolute value, and we can get root 2. And then we do the reparametrizing thing, and we get r of s equals this thing. And remember, in this question, it's r of s, s. It's not r of t. So we have to reparametrize it first, like this. So the equation of curvature is r prime cross r double prime, and then divided by r prime to the third power. So first we have to find r prime, second r double prime, we have to find the length of it. So this will become 1/4 sine square plus 0, 1/4 cosine square. So we can put this, take it out, into this. And this is basically 1. So we know r double prime is 1/2. And the curvature would be 1 prime cross double prime into the third power. And I'm going to skip for this calculating part. So at the end, it's going to be 1/8 cosine, 1/8 sine, plus cosine squared, 1/8 sine. And then this will be 4, 1/4 plus 1/4, 1/3. And after all the cleaning and everything, this will become this. And all the thing up here would become 64. And you clean it and then factor it, it'll become this, and then 1/2. Which is the same as the first one we had over here. So we can know this one's right. So for the second one, R of t, R prime s dot R double prime s equals 0. So we already know that R prime s is going to be 1 to the root half cosine 1 root s 1 root 2 negative 1 root 2 sine root 2s. And R double prime would be negative 1/2 sine 1 root 2 s 0 negative 1/2 cosine 1 square root s. And so basically we have to dot them together, right? And this will make it negative 2 square 2 sine 1 square 2s cosine square 2s plus 2 square 2 sine square 2s cosine s. And this thing is going to be equal 0 because this is actually the negative of this thing. So it crosses out. We get R prime dot R double prime equals to 0. So the third one and the last one is proving R prime s dot R prime s equals 1. So we know R prime s is like this. So it's basically just putting it in. Dot R prime s equal to root 2 cosine square plus sine 1 square s square. So basically this square will be 1/4. Oh, sorry. This will be 1/2. And then cosine square s. This would be 1/2. This will be also 1/2. Sine square 1 over square root 2 s. We know how to do this. We take it out. We got it cosine square something plus sine square something, right? And this makes it 1. Plus the leftovers, 1/2. 1/2 plus 1/2 equals 1. So you got it. We got 3 of the proofs done. This is a little lengthy, but I think this is actually one of the most important concepts and a really good application because it uses 3 different identities. Okay. So this is basically to show that exercise I actually mentioned to you guys at the first place. So it's basically the relationship between b vector, t vector, and n vector. It's not mentioned in the lecture paper, but I think it's super important, not really super, but pretty important to understand the concept of the relationships between these 3 vectors. So our main goal is get to d and ds, because we can't get to this point directly. We have to make it into small pieces, and then we put them together into d and ds. So the first thing we do is dt ds. You find what is dt ds, and then we make it going. So dt ds equals dt dt dot dt ds. This is like a chain rule thing. And then with times dt 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 on the denominator and numerator. And we put 1 dt dt absolute value over here and 1 down here. So it's basically just switching places. So it becomes dt dt ds dt and dot dt 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 absolute value. So this thing is actually the definition of n vector. And this thing is actually the definition of the curvature. So once we know that's the curvature and this is the n vector, we can say that this thing, dt ds, equals curvature times n vector, which is in that direction. So the second thing we have to do is to know what is dbds. Knowing dbds actually consists of 3 parts. The first part is knowing, because we don't know whether dbds is perpendicular to which vector. So we have to prove it's perpendicular to b, perpendicular to t. So we know that it's in the value of it's in the direction of n. So dBds, we can break it into the first part, dBds perpendicular to B. So how do we know it? We have to try to prove that the dot product of it is equal to 0. So this is a little side note over here. B dot B ds will become dBds dot B plus B dBds. And this two thing is actually the same. So we make it into 2 dBds dot B. And so we know dBds dot B equals 1/2 of dB dot B ds, like this. Okay, so this is super useful to prove this thing. Because once we know dBds dot B equals 1/2 of dB dot B ds, we know that B dot B equals 1 because B is a normalized vector. So when they dot it together, it will become 1. So once I know this thing is 1, then we know it's basically d1 ds. 1 is a constant and ds is a variable, so it makes it 0. So we know that dBds dot B is 0. So we know that dBds is perpendicular to B. Second thing, dBds perpendicular to T. So dBds, we can write it into T cross N ds dot T. We have to prove this equals 0. So basically, we do another chain rule over here, and then we move it into the denominator. Makes it r prime in the absolute value over 1. 1 over r prime absolute value. And this would be T prime N plus T N prime dot T. Remember this dot T at the back. We know T prime is curvature times N. So curvature times N, it makes it into the same direction. So the same direction, when you cross it together, it will equal to 0. And the second thing is T cross N prime dot T. This is this part. And since we know that T cross N prime is going to make a vector that is perpendicular to T. And when you dot it back with T, it becomes 0. So basically it's 0 plus 0 equals 0. So we got this proved. The last thing is the easiest, to know what dBds is. And since we know N equals B cross T, dBds perpendicular to D, dBds perpendicular to T, we know all these three, we can make sure that dBds is parallel to N. And dBds equals AN. We actually define this A into torsion. And why is there a negative sign? Because torsion is an action-reaction thing. That means it always go against it, which we have to add a negative sign. Oh, sorry. And then so we have dBds, dTds, and it's time to plug it back to dNds. So dNds consists of dB cross T ds. And then when we modify it, it's dB ds cross T plus B cross dt ds. We know this one is negative torsion N cross T, and this one is B cross curvature N, which is just replacing this and this. And by this diagram, this picture over here, we know that N cross T, using a right-hand rule, N cross T is negative B. And negative cancels out, it's positive B. Positive torsion B. Sorry, positive, torsion B. And this becomes B cross N. We use the right hand again. B cross N is negative T. So we put the negative in front, it's torsion B minus curvature T. So this is how we got dNds. Okay, so vectorial mechanics. There's 3 main points in the vectorial mechanics, actually 2. So the first one is momentum, P. And P is actually consists of n of m times v of t, and this is a scalar multiplication. And F is defined, the force is defined as the rate of change of momentum. And after opening up this thing, we know that F equals m dv dt. And the second thing is work. W integral a to b f of s. This is work, which is the dot product of force and distance. For non-changing forces, W work will be equal to F dot S, straightforward. And the third one is kinetic energy. KE equals 1/2 mv squared. The second one is dynamic of rotation. First one, torque. Torque equals R cross F of t, cross product of moment arm and applied force. Angular momentum equals to R cross P of t, cross product of momentum arm and linear momentum. And if this is constant, there will be no torque because torque equals d angular momentum t over dt equals 0. But how do we know this equals this? We have to do it over here. So basically, dl dt equals drt cross pt over dt. And so we open it up, it becomes dv dt cross pt times pt plus dv dt cross vt. We know this is v pt, and we know this can be dm v dt. After all the things, it becomes f cross r. And we know that torque is f cross r. And now we know dt dt is f cross r. In this case, we know that d angular momentum t dt equals torque. The second one about this chapter, about dynamics of rotation, is the central force. So the central force is basically just a scalar multiplication of your position vector. Because central force means the force which acts along the line of the position vector. Central force has no torque. Why? We can find out. This equals F cross R. And since we know F is C R of T, we know this thing equals 0. So there would be no torque. And here's a little example. So that for central forces, angular momentum is constant. And also if the angular moment is constant, the force is 0, or it is a central force. How do we prove that? Torque equals R of T cross F of T. And we know central force is F of T equals C of T R of T, where C of T is a scalar multiplication. So we put this back in, and we do the calculations. R of T cross C of T R of T. This thing will be 0. So we're pretty sure that F of T, we're pretty sure that our torque equals 0. And we know that dl t dt equals torque. Then we know the angular momentum must be a constant in order to make the derivative into 0, like this thing. So we got the proof. This is the last thing we have to mention in this chapter, quadratic surface. So this is the general form, ax squared plus by squared plus cz squared plus dxy eyz fxc gx blah blah blah. And with no cross terms, we basically just cross these out. This one, this one, this one. It becomes more tedious. Oh, I didn't finish it. And then plus gx hy. What comes after hg abc fg hiz my plus k. This is without cross terms. So these are the graphs, the basic graphs that you'll be seeing in quadratic surface. So the first one, ellipsoid. Ellipsoid is basically every side, every way you look at it, it's an ellipse. And so this is the formula. Second is the hyperboloid of one sheet. So basically, we if we want to know what these graphs looks like, we have to cover one thing, set it to 0, and see its projections on these remaining two axes. And for this one, we have a vase-like quadratic form. And hyperboloid of two sheets, this is one sheet, this is two sheets, is having a graph like this. Yeah, this is basically all just graphs and things. So this is paraboloid like this, and cone like this, hyperboloid, paraboloid like this. So basically, yeah, this is pretty much it. And thank you a lot for listening to our presentation. And I hope you guys can have a very good weekend and nail the Mosh finals. Thank you guys. Here. Okay.